In this video, we'll be looking at how we can use graphing technology, either a graphing calculator or Desmos, to solve more complicated inequalities. Anytime you're going to be using graphs to help you solve a problem, you have to be able to interpret it correctly. So, first thing is to look at this graph and know which graph is which. Based upon my work from earlier units, I would know that this blue graph looks like a parabola, and it seems to be that this red graph is an exponential function. And there are two intersection points, so this is going to create a double boundary inequality problem. Now we locate the intersection points. And so what I've done here is put in this green dashed line to help us visualize this region of this intersection point. And our job is to determine within which region is it that actually satisfies that inequality that we're given. So we have a region outside of this first intersection point, we have a region inside these two intersection points, and then you have a region on the outside to the right. And so based upon the original inequality, we will look at that to determine which region we're looking for. As we take a look, it is within these two boundary points, within them, that the parabola is greater than the exponential. And that's because that the parabola is above, so higher, greater than, the y values are bigger than the y values for this exponential within this particular region. So the parabola is above within that region. Outside these intersection points, we can see that it is the exponential which is above. Exponential is above the parabola. Some students do get a little confused for this part because the parabola kind of, quote, disappears, even though we do understand that it goes down forever and this exponential goes up forever. Students kind of get confused where the graph kind of stops, but you can see that the exponential is above for all of these x values, and it is above the parabola for all of these x values outside those two given boundaries. So that's why we kind of look vertically here with these dashed lines, because we're looking at each individual x value, which graph is the greater graph. Now we're given an actual example for these two graphs. And so we have 4 times 2 to the x minus 1 minus 3, which is greater than negative x squared plus 4. So that's what we're trying to solve with this inequality. We have an exponential and equal to a parabola. And so that is going to make it a little bit hard for us to solve it algebraically. So that's why we're going to go towards the graph. And so here we have the exponential, parabola, and we already know which graph is which, as we've talked about it before. But just to verify, this is our parabola graph in blue, and the exponential is in red. Next, we have to locate those intersection points. And so they're obviously where the graphs intersect, so you could use your graphing calculator to find those intersection points, whatever graphing tool that you use to find them. And so here we have negative 2.58 and negative 2.67 as our coordinate point down here, 1.36, 2.14 for this coordinate up here. Now, to be sure, this inequality only has x values, so I really only care about these x values. This y value is not important, and that y value is not important in our work. It's only an inequality based on x, so we'll only be using those x values. So we make a number line, negative 2.58 goes on it, and 1.36 goes on it. Now we're looking at that original inequality, which just says greater than. So when we're creating our number line, that determines whether these circles should be open or closed. The original problem does, not this graph. See, these graphs are both going to be solid because we're just graphing them on a graphing calculator. We're not dashing them or anything like that with any other inequality, because what we're using this graph to do is to help us solve this one variable inequality. So that's why we only care about the x, and it's based upon the original inequality that we use to determine what's going on at these points on the number line, so they should be open circles. So once we have those, we can continue with the rest of it, where we need to choose the region that satisfies the inequality. We're looking for where the exponential is greater than the parabola. So within these two boundary points, this is where the parabola was above, so that's not it. So it's going to be on these outside regions. And so we can see again that the exponential is above the parabola outside of those two intersection points. That means that we will be shading our number line to the left of the negative 2.58 and to the right of 1.36. And we finish by writing our algebraic statement, which is x is less than negative 2.58 or x is greater than 1.36. Again, there are two shaded regions, so there should be two inequalities that you write out, and that's all based upon your original inequality, whether it's open or closed, and then you have to look at the graph to see which region is it that satisfies that original inequality problem.